Hello, my name is Christopher Abbas, and I'm here uh, as a prospective representative from the University of Georgia in the ACI EcoConcrete student competition. Further, I am here representing my team as a whole, consisting of Simon Fox, Noah Kopp, Dylan Sopton, Guthrie Dean, Barry Zane, and myself, Christopher Abbas. My part, I will be discussing part of the decision-making process that went into creating our mixed design for the competition. Further, Dylan Sopton will be discussing the actual mixed designs themselves. And finally, Simon Fox will be discussing the LCA analysis, or the life cycle analysis of our mixes. In our case, we used the PCA 16th edition design manual in addition to the fixed volume method in order to be able to create our basic mixtures. After that, we had to decide upon our substitutes, what cementous material we would substitute into the alternative mixture. For the sake of economics, we decided not to consider silica fume due to its considerably greater cost relative to cement. Further, we were hesitant in using fly ash due to being unable to fully replace the allowed amount, in addition to some concerns with getting consistent results with it from what we were able to read. As a result, our alternate mixture uses solely blast furnace slag. With all that said, it's now up to Dylan Sopton to discuss the actual mix designs that we ended up getting out of our calculations.
The base case scenario mix design, 100% Portland cement was used as the binder material in accordance with the competition rules. A water to binder ratio 0.4 was used. This table indicates the proportions used in pounds per cubic yard. For the alternative case scenario mixture, 40% of the mass of the binding material was replaced by blast furnace slag for reasons outlined in the decision-making process slide. This reduced total water volume compared to the base scenario mixture. No air and training admixtures were used in this mixture. The adjusted weights are provided in the following table.
For our simplified life cycle analysis, the overall potential environmental impact has a negative score of 26% in every category for global warming, carcinogens, ozone depletion, ecotoxicity, and fossil fuel depletion. We tried replacing the cement with blast furnace slag to reduce the amount of cement needed for our concrete. All travel times we thought were within reason and not very far from the location of where the concrete will be put together. However, it was still a distance great enough to where the traveling time had too big of a negative impact on the environment. We were hoping that with the blast furnace slag, it would be able to replace enough of the cement. However, it still had a large enough impact. However, because of the blast furnace slag, it increased the amount of time that the concrete would be good for. The total years is about 18 years for the ACS. And because of this, the amount of work needed to keep the concrete up to standards would be less than what it would be if we didn't have the blast furnace slag. So even though it negatively impacts the environment, the amount of work over the years will not be nearly as much, and therefore, at the end of the 18 years, it would have a positive impact on the environment. We tried replacing the blast furnace slag with fly ash and silica fumes. However, the fly ash didn't really matter. It was about the same impact as the blast furnace slag. And the silica fumes would have had a great impact on the concrete itself. However, the pricing of the silica fumes is way too high, as well as the transportation effects on the environment. It would have been too great and left the concrete at an even worse percentage. This was Team Bearcat's concrete mixture. Thank you for listening. Have a good one.